All right. So yeah, and hey everyone, welcome to my talk. So this is Jinghao. Today I'm going to present our Rex framework and show you how we can design a kernel extension framework that's safe and usable. So, and a bit about the team. I was a PhD student at UIUC working on safe kernel extensions. There are many other folks who are part of this project, including Rowan from Red Hat, the Rosa Lab from Virginia Tech, led by Professor Dan Williams, the X Lab from UIUC, led by Professor Teng Xu, which is also the group I came from, and also people from IBM Research. All right. So in recent years, BPF as a form of safe kernel extensions has become particularly popular and seen a lot of use cases. So this ranges from networking use cases such as CDM and Catron, and to the tracing use cases represented by BCC and BPF trace. And people are also exploring new use cases of eBPF. So there have been research works applying BPF to storage and distributed protocols, as well as custom CPU scheduling and memory management policies. So comparing to other mechanisms of extending the kernel functionality, core to eBPF's value proposition is that it provides an unprecedented promise of safety. So in the mode of BPF, the developers usually write their source code or the extended program in a high-level language such as C or Rust. And then this program gets compiled into eBPF bytecode, usually by LLVM. This bytecode is then loaded to the kernel via the BPF syscall, and at this point, the kernel, the in-kernel eBPF verifier will perform a symbolic execution on all the possible code paths in your program and verify a set of safety properties. If the program passes the verifier, it is now accepted in the kernel and can interact with the kernel with a set of helper function calls. But if the verification fails, the program will be rejected, and the verified log will be sent back to user space. So the verifier verifies a bunch of important safety properties. Those include member and type safety, proper resource management, runtime safety concerning the program termination and stack usage, and the absence of undefined behaviors. However, it turns out the safety of eBPF actually comes at a cost of usability. So here, the example I'm showing on the slide is an example program from Cilium, which is a popular eBPF networking project. So what this code does is that it first looks up a service using a key, and if this lookup does not yield us anything, it's going to redo a wildcard lookup. However, this code does not pass the verifier. And what you got is like this huge chunk of verifier log, which is hard to decipher. It's all in BPF bytecode instructions. It's hard to map bytecode to the source code lines. And the actual error message is also confusing. It says invalid BPF context access, alpha equals 44, set 0 equals 2, but it does not say why it's invalid. And turns out in this case, the root cause is that the verifier does not really understand the compiler. And the program uses BPF H2NS to convert the indiness of the source port field of the program context argument. And this source port field is defined at the 32-bit integer, while the BPF H2NS only operates on the upper 16 bits. And when the compiler sees this, it's being smart. It says, OK, let's just optimize this code to only load the upper 16 bits. But the verifier checks this field access based on its size. And it's expecting a 32-bit load rather than a 16-bit load. And as a result, the program gets rejected due to the size mismatch error. And developers have to put extra effort to fix the problem, in this case, by adding the validate keyword to force the 32-bit load. So we argue that the core of the problem is actually a gap between the compiler, which is governed by a language contract together with your source code, and can employ whatever optimizations that are allowed under this language contract. And the BPF verifier, which performs the checks based on the different contract at bytecode level. So we call this gap the language verifier gap. So we already seen one such example where the gap causes problems. But the truth is that this language verifier gap actually has caused many problems. And based on our study on the popular and large eBPF projects such as Cilium, Katrin, IRS, we found that developers frequently have to implement workarounds to fix those verification issues. The developers often need to refactor their extension code into smaller ones to fit in the verification complexity limit. They may need to hint the compilers to generate verifier-friendly code. It's just the case we saw. They may need to hint and they may need to tweak their own code to assist verification, deal with verifier bugs, and even in some cases reinvent the wheels. So, a natural question, of course, is how we can solve the problem, and by closing this, language verifier gap. If we can run the kernel extensions without a verifier, then of course this gap will be gone. But that brings us to another question, which is like, how can we ensure safety? So our insight is that we can actually leverage the language part that already exists. Or in other words, we use the language-based safety together with a lightweight runtime mechanism. As an example, we can use Rust as our safe language, where we require the extension code to be written in safe Rust only. And then for the properties that are hard to be captured by the compiler, such as program termination and stack usage, we can actually implement the checks at runtime. So, and here we present Rex, which is safe, usable Rust kernel extensions. So in the model of Rex, the program is implemented in safe Rust only. It is then compiled by our trusted compiler, or trusted Rust compiler, of course, and linked with the Rex kernel crate. And this binary can then be loaded to kernel space. And at this point, the kernel will perform some load-time fix-ups to resolve the referenced kernel symbols, such as helper functions and maps. And after that, the program can just be attached like normal BPF programs and interact with the same set of helper functions the BPF programs can interact with. At runtime, this Rex runtime will provide support for safe exception handling as well as program termination. So here's an outline of the next part of the talk. I will first go over the compile time safety properties offered by the safe abstraction from the Rex kernel crate. And then I will move on to the runtime safety offered by the Rex runtime. So now let's first go into the compile time safety. All right. So kernel extensions apparently must access kernel memory safely. And in Rex, we divide this into two cases. And for memory owned by the Rex extension, our use of safe Rust actually already provides type safety and therefore absence of unsafe memory accesses. And this is further aided by this safe kernel interface provided by the Rex kernel crate for the cases where the extension program may need to send pointers to kernel. And for the memory owned by the kernel, those kernel objects with static sizes are again handled by the Rust type system. For dynamically sized kernel objects, such as packets, we use Rust slices, which provides built-in bounds checks. And this is actually in principle similar to the dynamic pointers in eBPF, if you're familiar with that. So in certain cases of kernel extension programming, there might be a desire to transform a byte stream into tabbed data. This is really common in networking use cases, but inevitably requires unsafe code under the Rust tab system. So let's take a look at the example. Suppose we have a packet payload, and we know that this contains a IP header, and we want to extract the protocol field of that IP header. And in C or BPF, what you do is you just perform a direct pointer cast, and then that's it. But in Rust, and especially safe Rust, you first need to downgrade this payload, which is a byte slice. You need to downgrade that into a raw pointer, perform the cast at raw pointer level, and then perform an unsafe dereference to be able to access its fields. And doing so, apparently, because it involves unsafe code, it apparently undermines safety. So you probably want to ask, then why would eBPF be safe in these cases? Well, it turns out for eBPF, it considers this cast to be safe under 2 rules. The first rule is that the cast should not make a pointer by casting a scalar value, which is basically saying like you cannot create a wild pointer from nowhere. And the second rule is that this new value must fit in the memory boundary. So in Rex, we follow the same 2 rules and extend the Rust type safety. And how we do that? And we first apparently need to avoid creating pointers from scatters. Our idea is that this compiler already has full knowledge of all the types. So we created an auto trait called Rex no-ref in the Rex kernel crate. And this auto trait is by default implemented by the compiler on types where all fields are already Rex no-ref. And in Rust, auto traits can also be selectively disabled on certain types via the negative implementation. And for our case, we added the negative implementation on all the reference and pointer types in Rust, which is shown here on the screen. And in this way, we effectively only implement this trait on types where there's no references or pointers. So let's take a look again at an example. So here we have a struct called myHider. MyHider contains this non-null U64, which contains a U64 pointer. And because it contains this pointer, it will not have an implementation of Rex no-ref. And consequently, myHider will not have an implementation of Rex no-ref either. So to use this to prevent casting a scalar into a pointer, we require the target type of the casting to be strictly Rex no-ref. And therefore, we will never convert into any type that may transitively contain a pointer or reference. And this satisfies the first requirement. For the second requirement, we implement runtime assertions that basically just checks the memory boundaries. So yet another important aspect of safe kernel extension programming is that those kernel extensions, they must manage the kernel resources properly to prevent resource leaks. And Rex leverages the resource acquisition is initialization pattern, or RAII, in Rust, which ties the lifetime of those acquirable resources with wrapper types defined in the Rex kernel crate. And these wrapper types will acquire the resource in their constructors. As an example, calling spinlock will just return a spinlock guard object, which represents a held lock. And the resources will be ultimately released in the structure of those of these wrapper types by implementing the drop trait in Rust. And again, going back to our spinlock example, the spinlock guard object will implement the drop trait and then release the lock in this drop handler. So the good thing about RAII is that the compiler already automatically inserts the drop call whenever the object goes out of scope. And there's no need to explicitly manage the resources. Well, with that being said, we actually found that there are several core library atoms in Rust that would interfere with RAII. And the notable ones are core mem forgot, core mem manually drop, core intrinsics abort. All of these prevents the proper execution of the destructors. And this abort intrinsics is even more problematic because it could additionally crash your kernel with an illegal instruction. So we forbid the usage of those language atoms in Rex by using the disallowed methods or tabs linter configuration from Clippy, which is the Rust linter. All right, so now we have seen how the compile time safety is implemented in Rex. Now let's move on to the Rex runtime. So it turns out that certain safety properties of Rust itself are already checked at runtime. So, and violations such as array out of bound access will just trigger Rust panics. And in user space, upon a panic, Rust will just perform the Itanium ABI-based exception handling, which will just unwind each stack frame and execute the cleanup code on a frame and going to the next frame. However, doing so is actually not suitable in the kernel because stack unwinding in kernel space cannot fail. Otherwise, we may risk leaking resources or even crash the kernel. And at the same time, executing user-defined arbitrary destructors is not safe because we cannot ensure that those destructors do not trigger a secondary panic that will fail the whole panic handling process. So in Rex, we support the safe exception handling in two components. We call it graceful exit and resource cleanup. So let's first take a look at graceful exit. So here, on the left-hand side of the screen is the in-kernel dispatcher function of Rex, which is responsible for invoking the actual Rex program. So this function is entirely written in assembly. The first thing it will do is, after entering this function, it's going to save the old stack pointer before the program invocation. And then it will call into the program. And if the program ever panics, our panic handler, the Rex-specific panic handler inside the Rex kernel crate will be called, which will clean up the resources and then jump to the in-kernel Rex landing pad. This landing pad will report the error message to the kernel console, and then jump to the Rex exit label back to inside the dispatcher function. And at this point, the dispatcher function will just restore the old stack pointer, which effectively just reset the whole context and effectively unwind your stack. And for the sake of better user experience, we also integrated this graceful exit mechanism with the kernel stack trace, where we just dump the stack traces of Rex panics to the kernel console. To do so, we registered the mangled Rex symbols and into the KL sims upon program load. We also enabled the frame pointers in the Rex programs to allow the kernel stack unwinder, especially the OR unwinder, to correctly walk the stack. And in this way, the user will get traces like this upon a kernel panic, the Rex panic. So we can see that this exception comes from unwrapping a non-value, and it happens inside the injector function, which can help the user to pinpoint what went wrong much easier. All right. So the other important aspect, as I mentioned, of safe exception handling is that you must properly clean up the acquired resources to prevent resource leaks. In user space, again, the Itanium exception handling ABI uses dwarf information to identify all those acquired resources. But our insight or our observation is that it does not need to be so complicated in kernel space, and especially for kernel extensions, because those extensions can only acquire the resources via helper functions, and only these resources need to be released. So Rex just records the resources allocated by helper functions, provided by the safe abstraction of the Rex kernel crate, into a per-CPU buffer. And upon a panic, the Rex panic handler will just iterate the resources and perform the needed cleanups. So, okay, perhaps one of the special requirement of kernel extension or kernel programming in general is that you should never overflow your kernel stack, because unlike user space, those stacks, they do not grow. And stack check from eBPF is apparently still done by the verifier, but it has since been shown that those could be compromised by combining BPF tail calls and BPF to BPF calls. So in Rex, we divide the stack protection problem into two cases. For the extension programs that does not have any indirect or recursive calls, its static call graph will just be a DAG. And this allows us to easily compute the total stack usage statically based on this call graph and perform the check at compile time. For the extension programs that does have indirect or recursive calls, apparently your static call graph may not be a DAG, and it may have unknown nodes because of the indirect calls. So Rex will just opt for a dynamic approach where we insert compiler checks to the before each function call which will be executed at runtime. And a failed check will just trigger a Rust panic, which will be gracefully handled by our exception handling mechanism. And the last safety property I want to talk about is safe termination. And apparently it's important because a non-terminating extension could just hold the CPU for a long time. And then it's just preventing other tasks or interrupts from being executed. In Rex, we use a dynamic timeout mechanism for the termination support, where we just set up a high-resolution timer on each CPU that triggers periodically. And because those timer interrupt runs in hard IRQs, that can just preempt programs running in soft IRQ or task contexts. And if there's a timeout, the Rex runtime will just set the program instruction pointer to a timeout handler inside the Rex kernel crate, which will in turn trigger a Rust panic to terminate the program. So one caveat is that if the program is currently executing a helper function call, which means it's currently running the actual kernel code, we need to defer the termination until that helper function returns. This is because kernel code has its own state management, and doing so, and if you just naively terminating the program when it's running a kernel helper function, that could easily lead to inconsistent states, and for example, dangling ref counts or unreleased locks. All right. So implementation-wise, we implement Rex on the latest stable version of Linux and Rust, which is currently Linux 6.15 and Rust 1.87.0. But we just keep rebasing the changes whenever new releases are rolled out. The Rex kernel crate, as we mentioned, it implements the safe kernel interface for the Rex programs. Those includes the kernel symbol bindings, which are implemented manually and are emitted as relocations in the compiled pi binary of that Rex programs. And there are kernel data type bindings, which are automatically generated by bindgen, including the kernel struct types, the constants, as well as type aliases. And finally, it also implements the program-specific code, which provides supports for 5 existing BPF program types. And we currently support kprobe, perfiment, tracepoint, XCP, and TC. So inside the kernel, we implement the program loading and the symbol resolution mechanism, where we just, because we don't have the verifier, we just map the program into the kernel address space. And we patch the global offset entries for those referenced kernel symbols. The Rex runtime also lives in the kernel, which consists of the stack count vendor, which is for safe exception handling, and the termination timer handler. We actually also added a small LLVM pass to the backend of Rust C. This is for performing the Rex-specific instrumentations, for example, stack checks. This pass is currently also responsible for generating the extern C program entry points. But we are actively moving those to proc macros so that we can just reduce the changes and the complexity of the compiler. All right. So we evaluate Rex on its usability, and apparently there's no verifier anymore, so we no longer have that language verifier gap. We used Rex to implement the BPF memcache dcache, or BMC, which is a fairly complicated, I would say, BPF program that implements a kernel-level cache for memcached. On one metric, which is lines of code, we found that our Rex program is just 300 lines of code versus the 500 lines of code of BPF C code. And in general, it's just much cleaner and simpler. We brought Rex into the OS classes at UIUC. We designed 3 assignments on kernel tracing and networking, and we found that our undergrad students are actually able to write correct Rex programs. So now, let me use the BMC cache invalidation logic as a case study of the usability improvement. So here, the snippet is a part of the BMC's cache invalidation code, which this particular code searches for a set count, not a set comment, but a bunch of set comments inside the payload. There are several things to notice. So the first, the developers had to add additional limit, which is called BMC max packet length, to limit the number of iterations of this loop to fit in the verifiers complexity limit. Because the eBPF verifier requires explicit bounce checks, you got a lot of boilerplate code to just check the end of the packet. And finally, it requires a highly verbose logic to match the set comments in the payload. Well, if you were to rewrite this code in Rex, it would look like this. So the first thing we'll notice that there's no extra code to handle that complexity limit from the verifier. And we have the Rust slices, which already provides us the implicit bounce checks in this method, so we no longer need all those boilerplate code. And the built-in methods of Rust slices allows easy match of the set command. So to conclude, it's just much cleaner and simpler. We also evaluated the performance of Rex. In this plot, we varied the number of CPUs assigned to the network interrupts and the memcached server. And we measured the max throughput of 3 settings, which is pure user space memcached, represented by the blue bar, the eBPF BMC, represented by the orange bar, and the Rex BMC, represented by the green bar. So the takeaway is that Rex's safety and usability does not come at a cost of performance. And it was actually able to achieve a 5.4x speed up over the user space memcached on 8 CPUs, and we got a slight, which is less than 5%, performance benefit over eBPF. And we attribute this to the simpler code as a result of the better usability, as well as the better optimization provided by the Rust compiler over the combination of LLVM and eBPF JIT. So to conclude, static verification in kernel extensions may lead to poor usability, as we saw in the case of eBPF. Our insight is that we can leverage language safety together with a leverage runtime mechanism to provide the needed usability as well as safety. And we realized this design in Rex. We found that Rex can deliver the usability without losing safety and performance. And actually, our code is open sourced. You can find it through this GitHub link. And yeah, that's the end of my talk. I actually also want to do a small demo. So let me see. All right. Is this font large enough for people sitting in the back? All right. So, OK. It's not on my screen, so I need to. All right. So let's first get to the server, and I think I have a ZEJ session for this. Here we go. So yeah, the example program I want to show you guys, it's a simple kprobe program that injects a given error for a given syscall to a given process. Yes, there are like 3 variables here. And here it's like the code of the program, which you can see on line 11, we define a BPF map. Yes, Rex still reuses the BPF map infrastructure. We define a hash map that basically contains a pair of PID and kernel, which is the process you want to inject your error in, and also the actual error to inject. And this program is defined as this error injector function. You can see that we have a proc macro here called Rex kprobe, and so that's the Rust proc macro, which operates on the EST level, that does code transformation to generate the program entry points. So what this program does is you can see that it's first grabbing the current task, and then it tries to get the PID of the task, and then it tries to look up the map to see if you have a PID, if you have an kernel defined for that PID. And if that's the case, then it will do the last step, which is just do BPF override the return to override the return value of that syscall. And so all this, the PID, the process, the kernel is it's supplied by the user space loader program, which is here. It's so you just pass in the syscall and the kernel from the command line, and then we do Rex object load. That's a special loader function from our loader library, which is built on top of BPF. And you can easily get a BPF object from that by doing Rex object get BPF. And then you can just use the regular BPF APIs to interact with the maps, the attachment point. You can see that we here attach to the cases call of the syscall you pass from the command line. And then we do here, in this program, we do a fork where we just send the PID of the child into the program along with the kernel from command line. And if you run this, I'm going to start the VM. So if you run the loader, let's say, I think I had a hard-coded syscall, which is stoop. And let's say we give it kernel number 22, which is invalid argument. And if you do that, it says invalid argument. If you give it 23, I actually don't know what 23 is. But apparently, it's too many open files in the system. So that's a normally exited Rex program. So what if we have a panic here? So now let me just comment out this code. And then if we go here, I have another piece of code which, instead of doing that OK or monadic operation on the option, we just do an unwrap. And unwrap will panic upon a non value, as we all know. And to get that non value, we also need to remove our entry for that program inside the loader from the map. So basically, we just skip the map update element part, which basically sends in the kernel and the PID. We comment out that, but we do need to uncomment this line. Oops, where am I? I think it's here. We do need to uncomment this line because otherwise the compiler is going to be mad at me. All right, and then we just recompile it. Let me see. I probably shouldn't use time-wait, but that's fine. Takes a little bit because this lab machine is not powerful enough. All right. So we restart the VM, and we go into that program directory. We run the loader, let's say dupe22, and what you get is something like this. So if you scroll up, you can see Rex panicked at source mean, line 26, character 10, called option unwrap on a non-value. And because we integrated the exception handling with the kernel stack convenger, you can get these stack traces, which goes from dump stack to landing pad to all those panic handling things of Rust internals, and back to the unwrap field, and eventually our injector. And the important thing to note that the kernel is still alive. It does not kill the kernel. And yeah, that's the end of my talk, and I'm happy to take any questions. Yep.
The verifier in the kernel, the way that it is currently set, as a person running the Linux kernel, I don't have to trust eBPF code to have some properties. Now, if we're removing the verifier, how does that influence the trust that we put onto eBPF programs? And I think the more important question is, can we keep the verifier and just add functionality to it to support this use case?
Yeah, that's a good question. Let me quickly repeat that. So basically, sorry, what's your name?
John.
Yeah, John was asking, so apparently, because we have that in-kernel verifier, we don't need to trust anything that's basically outside the kernel. And but here in Rex, we removed it. How would that even work trust-wise? And also, can we just keep the verifier and instead improve it? So yeah, that's a good question. I think for trust-wise, I do admit that as a trade-off, we now need to trust the Rust compiler for its safety properties. But I would also point out that the same trust is just universal in the kernel. You do trust your C compiler to generate correct code. In Rust for Linux, you do trust the Rust compiler to uphold your safety properties.
But I trust whoever, maybe I'm trusting Ubuntu to compile my kernel. I don't know if I trust whoever compiled the eBPF code, but I still want to have the guarantees that it's not going to crash my kernel.
Right, so that's a good question. So let me repeat. So apparently, you can trust the one who boot the kernel, but you probably don't want to trust the one who just compile the program and load it, right? And so I think another important point to note here is that BPF has already moved away from an unprivileged use case. So I would say that's effective moving towards a non-adversarial model. And therefore, we sort of just follow that model, and to load the Rex program, you actually have to have the capsysadmin. So I would say that's probably enough for you to trust that guy. And if you want even more, more trust, we can try to do the same thing where the BPF folks are trying, which we actually got a talk yesterday on that. Which is you just sign your program. And then after you load it to the kernel, you just let the kernel to verify that signature. And then in that way, you can establish that chain of trust. And then to your second question, which is, can we just implement this thing as a sort of an add-on on the verifier and instead keep the verifier? I think that's could be. I mean, I would first refer you to, there's a really nice talk from Kumar at last year's LPC, which is talking about fast and flexible kernel extensions, which they just built an SFI mechanism on the verifier. Yep. All right, and any other questions? Yes?
So you mentioned frame pointers. Do you have to build the kernel with frame pointers to use this?
All right, so Jonathan was asking whether we need to build the kernel with frame pointers. The answer is no. So I mentioned frame pointers pretty much because we want to integrate to allow the kernel stack unwind which org to unwind our program stack. The thing is that if you know how org works, it's basically using some debug information extracted by obj2 to basically ask metadata to identify the program stack. But apparently that would not work for generated code, which is BPF and Rex. And BPF is already using frame pointers. And for us, all we need to do is that we need to build the Rex programs with frame pointers, but not the kernel. The kernel can still use the whatever debug information the obj2 generated, but when it's looking at our frames, we have the frame pointer which provides the information. All right, any other questions? All right, yeah, thanks for attending.